many people in the room actually have ever heard of ETAP before? Okay, a couple of people have been to our office. Great. Well, what I'm going to do is I'm going to go through a real quick introduction on ETAP and the technologies that we provide, and then go right into the demo application. So again, if you look at ETAP as a company, we have over 200 employees worldwide, with about 140, 150 of them located in Southern California. We're the largest developer of, we're a design tool. We're a little bit different in this environment, where we're the type of tool that the engineers use when they're designing and building power system networks. They're going to use us to size the cables, to size the transformers, size all the equipment, do the protection schemes. And then we're getting more and more involved in the industry because of the generation of renewables into the electric networks. We've been around for 27 years, plus 27 years, so we're not new to the business. We've been developing software at that rate. We grow at about 25% a year. And we have offices all over the world. So we're located in all the major countries. We have 4 offices in China, 4 offices in India. We're in the Middle East. We're in South America. So we pretty much cover the globe. And again, we have 2 different groups within the organization. One is primarily the software development group that we use to develop our software. And then we have a solutions group. Because what we're doing is we have what we call our offline tool, which is used primarily from the design perspective. And then we have our real-time tool, which you can take the same design model and bring it into real time. Okay, and actually can be used from an operational perspective. Again, some of the industries that we work in, anywhere where power networks are a large part of the operation. So consulting firms are probably our biggest customer, consultants who use our tool. But we're in any mission-critical area where power is important. We also work in the university space. We have over, I think, 65 power labs throughout the world where we actually donate software to universities. So the professors can actually teach theory and practicality in the same curriculum. One of the things also is unique, we have over 50 modules for design and analysis of electrical power networks. So the nice thing about ETAP software is if you're only doing a certain type of analysis in the system, you can just buy the modules that you need. So you kind of buy them in an a la carte fashion. As you grow your business or you grow your analysis, you can add more ETAP modules. One of the things that we actually have also seen with renewables is we have a whole new ability to handle renewables. All these new things about battery technology, solar, wind turbines, they're all kind of new as how they're going to be applied to electrical networks, and we help you model those. Our real-time application takes the development tool, hooks it up to information coming from either an electrical SCADA system or a network or a simulator, and bring that real-time information into the model, and then you can do analysis on it. We also have an ETAP grid, which is sort of new from the standpoint of how we package the tool, but now we're working in both distribution management systems and transmission level grid applications. The ETAP grid tools also integrates GIS functionality. We have an Esri-based system or an ArcFM type GIS. You can now bring that GIS information and have a geospatial relationship of the electrical model. Again, just to kind of show you all the different, they're broken down into different types of studies. But we have everything from network analysis, the real-time systems, GIS mapping. Data exchange is, again, another tool we can convert just about anybody's model in the industry into an ETAP format. So if you have a PSSE model, SKM model, dig silent, we can report that information into ETAP to work within our environment. We have control systems for battery systems, cable pulling, if you have to do any cable pulling calculations, bend radiuses, underground raceway design, thermal ampacity calculations. This is also very important. This is something that comes into play. We have a user-defined modeling application. So if you already developed a model in Simulink or MATLAB, you can actually bring that model into ETAP, convert it into our language, let's say, and we can use it and links to all our analysis modules. One of the biggest benefits that we're trying to bring to the industry is when you're hired to come up with either simulation or design, you don't want to spend all your time trying to make the two work. Okay? What you want to do is you want to be able to build a one line, define all the components, and get right into the business you were hired for. Not trying to get this part to talk to this part, moving forward on it. So this is just what we call our offline modules that we utilize. In our real-time systems, we can take the same network environment that you've designed and sold to your customers and bring it online. So now we can do energy management systems, do generation control, automatic dispatch, load frequency control. We can do substation management. So if you want to scale down and just do this analysis just at a substation level, we can provide that functionality also. One of the also things we do is really important in the industrial market, and same thing with the renewables, is intelligent load shedding. Okay, what we do is we do predictive load shedding. So we analyze the electrical network. We understand what the impacts of shedding certain loads at certain times are going to have on the system. We pre-program that into our load shedding controllers. So our load shedding controllers don't have to calculate what needs to be done. They already know what needs to be done. So when something starts happening in the electrical system, we're taking action already. We've proven through validation that the actions we take aren't going to disturb the electrical network. So it's very high speed and very repeatable. And then we're also into the distribution management system, because as you scale up into distribution systems, it's really an industrial system expanded a little bit larger. We can handle the feeder, restoration of feeders. We can do outage management type of applications. And probably one of the biggest, fastest growing things that we're involved in, and one of the things that we actually contacted OPAL-RT about, was microgrid master controllers. Because all these different utilities and even the Army, the Navy, the military, are all interested in microgrid controllers. Being able to take renewable sources, island the systems, maintain the operation that they need for their critical loads, and then share that, share the power between the grid and being off the grid. So a microgrid controller, you have to have the ability to simulate that. And again, we can design it with our tool, but now with the connection to like OPAL-RT, which has a field simulation of the actual network, we have end-to-end simulation. We can actually go through and do what-if scenarios using our tool from a design perspective, send our commands out to a simulator like OPAL-RT, feedback comes in, now you can tune and optimize these microgrid controllers. So you have a complete solution using the tool that you're going to deploy and the design you're going to deploy in the field, actually with a simulator, to make sure that when you're delivering this thing to one of your clients, you can by no means take any data out of their mind the operation of this system moving forward. And what we're going to simulate a little bit today is just one application that we have of many, is our automatic generation control, where what's going to happen is we're going to simulate a load change on an electrical network, and our AGC is actually going to go out and bring the frequency back up to where it needs to be. I mentioned a little bit earlier about our ETAP grid. Our ETAP grid application allows us to work on larger distribution and transmission systems. It allows us to create equivalent circuits in a geospatial relationship. So now we can actually take large networks and then bring them down to their equivalent circuit components and solve them much faster. It also allows to give our users a geospatial relationship with, so when you have a fault somewhere, you want to geospatially understand where that is, dispatch trucks, or actually put in fault restoration schemes, you have a much more graphical representation of the system. And again, you can take that and again bring that right into a situational awareness, whether you want to deploy that information on the web or actually put it into some type of HMI compatible system. The other thing people don't realize about us, we're the only software for design that's certified by the nuclear industry in the United States. We have 97% of the market in the US that uses our tool. And because we're nuclear certified, that means that we have to go through a very rigorous validation and verification process anytime we have a new release. We try to put out one new release per year, which has functionality and features that our customers request. But anything we put out has to be validated and verified through a procedure that we have. So we can never issue a bug fix. We can never issue a patch, right? We have to go through a series of tests. And you as a customer, even though you don't buy the nuclear version, you get the quality that comes with that. You just don't get the right to audit us 4 times a year for compliance. Unless you want to pay for it. And again, this is back to our quality assurance program. We developed this in 1991. And again, all of our software libraries, all of our software code is validated and verified. Okay, so one of the things that we can do is that we can accept people's information into the library, or you as a user can use whatever models or whatever libraries you have, but to make it into our software, it has to be validated and verified per our QA procedures. And again, what this does is it keeps us organized, okay? But it also sometimes delays releases that you have moving forward. A lot of times what we'll do is, right now we're at version 12.6. 12.5 came out probably 3 months ago because we had to get a version out to meet certain requirements for customers. We came out with another release, 12.6, was all the things that we couldn't get verified and validated in 12.5, we put in 12.6. So it's always a process of continuing improvement. Again, we mentioned earlier, 50,000 licenses worldwide. If every one of our licensees created one model, we have over 50,000 models around the world in ETAP. Okay, so it's a very well accepted tool. 5,000 plus companies, it's their standard. It's the only tool that they will use. Some of our other customers will actually use our tool to verify tools that they have. So it's been very well accepted moving forward. And again, this is really important. We listen to our customers, so 95% of the improvements we have come from people who use our product and use our tool. Just to show you a couple of the major EPC firms around the world that standardize on ETAP. Some of our oil and gas companies, we work with all the major oil and gas companies because they have large electrical networks utilizing ETAP. Transmission distribution companies and also generation companies that use our tools for some part of their electrical network analysis. And the other thing also we found out, and again, sometimes we don't even know they're using it, we're involved in a lot of these NSA facilities that we can't talk about have all used our tool, and actually some of them are using our real-time application to make sure that the uptime on these facilities are going to be there, and also from a predictive simulation perspective. And one of the things I want you to take away from this is we're really envisioning ourselves as a complete life cycle solution. To go from a design environment to an operation environment, back to a maintenance, back to the cycle again. Because we believe the electrical model is the most important asset you have in a power system. And if it's going to be accurate, then you could use it over and over again. Too often what we found, even in the past, that firm A designed it, firm B built it, firm C had to operate it. By the time it went from 1, 2 to 3, the fish, the cat that they got, you know, was completely different. And what happens when you have a problem when you're trying to enhance it, the first thing you got to do is validate if the model's correct. And that wastes time, because now you're even, before you can solve a problem, you have to figure out, make sure your watch is set right. We're trying to eliminate that. And one of the reasons, and one of the ways we came up with, if we can put that electrical model from the design desk in front of an operator, in front of an operational environment, he's going to want to count on it for it to be accurate, so the whole chain now completes itself. So then when they go in and want to expand the facility, they take the same operational model, they go into planning, and then start the cycle all over again. So one of the things we're going to be showing you today is sort of a real-time, the real-time application we have moving forward. When we get into the demonstration, I'm going to just go ahead and quickly show you, and this is the same thing that you see, I think, over here. I won't bring it up. But the model, you see everything in blue right there is real-time data coming in from the field. Meter data coming in. Actually, let me pull that down. This is our AGC application. But all this information right here is real-time data that we're collecting from meters, from phaser sensors, everything that we can bring in from a data collection system, we can bring into our ETAP model. The values you see in the red are calculated values. We have an online running state estimation engine. So if we can't meter our whole network, but we can put boundary meters around that network, we can estimate the power flows in between, which becomes very important when you can't afford to meter everything. The other nice thing is also we can do situational awareness. If something happens over the weekend, we can collect the data through a historical system and then play it back graphically. We get like a DVR control. So now you can step through seeing what happened, then play it back and change something in the predictive simulation mode, and this is what you should have done. So you can actually make it an operational training tool. The nice thing about it too is, you know, let's say you're using it as an HMI screen, it may have too much detail on it. But if you're an electrical engineer and you're having a problem on this, you went over here and you happen to click on a transformer, wait a little bit, come up. I have all the operational data or actual physical data of that transformer that it was designed with. If I need to look at the impedance on it, the tap changes, the grounding, this is all at my fingertips, all right? Imagine if you walked into a site and you blew up that transformer. You had to go out and find out all the data. You get on the phone, you can't find one exactly like it, but you can find one on either side of it, possibly. Right now, what you could do is we could go right into predictive simulation, plug in those new characteristics of that transformer, take a snapshot of real-time data, run some analysis, and let us know if we can live with that before ever having to order it, that type of information. So it also has kind of a built-in asset management function of it also. Also a nice thing about even having this at your fingertips is now you have asset information about the model, you have real information and from a maintenance perspective also moving forward on. So what we'll go ahead and do here is we'll go ahead and get into the demonstration part of this thing. Just to kind of show you right now, very simple. We have an AGC view up here right now where we have 3 generators running. And what we're going to end up doing is the lead's going to go ahead and interrupt the load, make a load change. And what AGC will do is it'll notice that change and then increase the set point down to the generation controllers to bring the frequency back up to where it needs to be. And this is just one of the many applications that we have from a automatic generation control aspect. We can also do economic dispatch. So we can also set up goals and rules. If you had interchange scheduling contracts where you had to buy or sell power, or you wanted to be able to meet power requirements based on minimizing fuel, minimizing losses, all that type of information, you can set up the control algorithms, and the system itself will go ahead and take care of it. I'll go ahead and turn it over to you to run the demonstration. And I guess, no, that's the end. You changed that one, so we got to go a different way.
So what do we have here? Okay, so what do we have here? We have the ePHASORsim model, which is actually the RT lab. It's the, as you may know, that it's do the phasor type simulation. And then we have the ETAP here, which does the online calculation for the AGC for automatic generation control, in which the demo that we are presenting here right now. And then just to communicate between RT Lab and ETAP, we are using the Kepware as the OPC server. Because RT Lab is running on the RT Lab model is running on the Linux machine, and ETAP is running on the Windows operating system. To communicate between these two, from RT Lab to Kepware, we are using the DMP3, and from Kepware, between ETAP and Kepware, we are using the OPC. So this is the schematic of briefly explain that what we are doing here. We are making the model. Suppose that you make your model in the ETAP, and then we can make it also in ePHASORsim. Then we can transfer the the bus voltage, the active power, the reactive power, and the frequency from the ePHASORsim. We send them to the OPC server. The OPC server transfers this data to the AGC application, and AGC does the calculation and sends back the set points for the mechanical power, for the mechanical input power of the machines. And if you have the ETAP monitor mode, you can also see, you can also visualize some of these data in that single line diagram as well. So actually, this is my demo that I want to show here. The system that I am running here is the 9-bus system, actually 9-bus system. Here, this figure is borrowed from the ETAP view, ETAP monitoring view, and it's just a picture here. But we can have some displays to show the voltage and the other controllers, for example, change of the loads or change the tap position. And we can add other type of the parameters to visualize. Here at this place, I have the data that I am sending to the system data, which I'm sending to AGC. It's as I showed in the other slide, it is the bus voltages, active and reactive power, and the frequency of each synchronous machine. And then AGC sends back the set points power for each machine, along with the dispatch signal. But the dispatch signal means that these calculations must be applied to the generator. Please correct me if I'm wrong. Okay, so what happens here that normally this is a tough part because of unstable communications that I have here. I was not able to connect this. I have 3 generators here, but the 3rd generator, for some reason that I don't know, is not sending that. It doesn't transfer the data through the Kepware. So you see that here I have the G1 and G2 that are sending the data to the OPC server and getting the data from there, but this one is not doing that. So if my model, I connect it to the AGC here. Actually, what I will do, I put ETAP on that screen so we can see it easily.
And we decided to use OPC for this demonstration just as a choice. A lot of times customers will have existing SCADA systems already, and we just make an OPC connection just like they're collecting the data. But we also have direct 61A50 drivers and DMPV drivers that can be configured to talk to the two systems.
Okay, so I will, right now you see that the system is stable. The frequency is almost 60 hertz here. You see that the average frequency, I have 370 megawatt of the generation and 310 of the load, total load in my system, just the active power. So what I will do, in the AGC you can have two modes, the supervisory and advisory. In the supervisory, whatever which is calculated is ready to send to the through the OPC server, but in the advisory you need to, it just gives you the value, then it's based on the operator decision that if he wants to apply these changes in the system or no. So here what I have is the supervisory mode in the AGC view. So I just put my AGC here in the supervisory and I connect to AGC. But I see that you see that right now, because the generator tree is not connected, the frequency is not stable. It's not trying to, it cannot make it stable because one of the data is missing here. You see that generator tree is missing, the set point is not there. So I owe you a demo. Maybe when you visit RT OPAL-RT tomorrow, I can show you there at office. Maybe I can work on that. But I have a video here that I just run the video here. So this is this is exactly the same situation here, that you see that I have all the three data here. You see the frequencies around 60 hertz. I connect to AGC. I'm in supervisory mode, and here what I will do is that just let's. This is the data which is coming from the RT ePHASORsim, and I am in supervisory mode. Okay. So sorry, it's a bit messy because I just made it 1 hour ago for this for today. So I'm changing the load. You see that when you change the load, the frequency is maybe here. You see that I changed the load in the RT lab in ePHASORsim. You see that the frequency, I increase the load, so the frequency goes down. And then the AGC tries to make the new set points for the power. You see that the target is changing, and then it increases the power to compensate for that load. So now the frequency again is around 60 hertz.
How much should you change the load?
Probably 10 megawatt or 20 megawatt. Yeah. So this is another, I'm increasing the load here. You see here I'm increasing the load. The frequency starts to goes up, and then AGC will bring back the set points to the normal frequency of the system.
So what this allows us to do when we actually deploy this for a customer, we can have an end-to-end simulation where now they can go through a bunch of different scenarios, and you can tune and optimize the AGC. Everybody understands what the results are going to look like with the generations without stressing the generators up and down to go through the scenario. So what it also does for you, if you're delivering this as a solution and you're trying to get signed off on a factory acceptance test, right, you can actually go from this type of a simulation out to the field, and the results should be the same moving forward on it. And the nice thing too is we're going to model the generators in ETAP the same way that, from the manufacturer data or from our libraries to put them in there. So, and the other thing that we also show, since we're calculating values and reading values, we can also make sure the model that we're working with is accurate. That's one of the first steps in this whole process, that when we take a model into real time, we want to make sure that the reading values and the calculated values are within a certain deviation. And we also have the ability to alarm off of that. So if a meter starts to becoming either inaccurate or maybe a CT's loose or something like that, all of a sudden you get a deviation alarm. You might want to know that if you're trying to optimize off those readings. And it gives you that kind of an alert and alarm.
Yeah, thank you. So that's that we have here. Actually, this is more explanation about the AGC and the fundamental of that. What we have normally for each generation unit, we have the control for the reactive power and voltage, and also we have control for the active power and the speed. So I guess everybody knows what is the governor is doing, that it tries to create, based on the change in the load, tries to increase or decrease the speed of the machine to keep the frequency in the nominal frequency. And here what we have the EMS part, which is do this type of calculation like AGC or economic dispatch or intelligent load shedding. Normally needs the data from the system for this type of a calculation. So in this demo, what we show that the system is running on the ePHASORsim, and and then the EMS part of the ETAP does the calculation, and they are communicating together. So if in this case we are sending the data from the generator data, and here we are getting the set points for the governor block of the synchronous machine. Okay, as I am a moderator also, so if you have any questions, otherwise.
We threw a lot at you in the last 20 minutes.
Yes. So you have 5 minutes for question and answers. Yes, sure.
You said he's the moderator, you can't ask questions.
I'd like to go back to the slide where we can see ePHASORsim, the OPC, and the BIS connection. I'd like, if you can, again, explain exactly what is this interface, how?
Okay, let me this one. See, we have the model, our model RT lab is running on the Linux system, which is there, okay? And then we have ETAP, which is running on the Windows operating on this machine, on this machine.
What is the application running on RT lab and the application that is running on the grid? What part is running on ETAP?
Okay, here in RT lab we have the ePHASORsim model. We have the power system. Okay, we made it in ePHASORsim, so it's the ePHASORsim running there. Then we use the DMP3 driver to create the data, to package the data in the DMP3 format, and then we send that to the OPC server, which is, in this case, we are using Kepler. Actually, it's a temporary solution for this case. Otherwise, we have to use the OPC server of ETAP. Okay, and in the ETAP side, what we have the AGC application, which is running on the Windows machine, and it is not real time. The same concept that we are talking in our own, that it's computation must be.
AGC stands for
Automatic generation control. Yeah, we're using a lot of the same words, but they have different meanings. We have the same model running in ETAP. Okay. It's designed the same way as the one that's running on ePHASORsim. It's the same bus model. What we're looking at, though, is the characteristics of that model from the design perspective, and we're also, normally we'd be feeding also metered information from the different meters inside the system also. And what we're doing is the OPC just allows us to map tags between the two pieces of software. It's just a standard in the industry that anytime you're connecting any type of SCADA or third-party systems, it gives you the common tag mapping protocols for it. It's a way, it's not the way. Usually probably you'll have a direct type of driver communications for that, using one of the standard drivers that are out there in the industry. But the goal, I guess what we're trying to get at to is eventually come to a place where you don't have to build it here and build it here. Right? You build it here, we can export to XML, you interpret that, and you have the same characteristics. Because that's where the real value comes in, to the end users, is not having to do it twice. Because when you do it twice, then you have to check to make sure they're both the same. And that's what we're trying to get away from. And we've already got 4 customers who are doing microgrid solutions that are both looking at OPAL-RT hardware and ETAP as a design tool. So now what we're trying to do is say, look, we can save a lot of effort of trying to make it work by taking this model, being interpreted in the simulation, and have an end-to-end simulation that you can test everything before you go live in the field. Okay. Thank you.